Welcome to the Basics of Intrinsically Safe System Design by PR Electronics. Hopefully this 30-minute presentation will give you a taste of some basics of intrinsic safe design. PR Electronics has been a world leader in intrinsically safe barriers since 1974. We manufacture the products, we have our own R&D, and we're one of the leaders in new engineering concepts. So we know a bit about this. All right, before we dive into intrinsically safe system design, just a quick look at some of the other product lines that PR offers, from head-mounted temperature transmitters through multi-function rail-mounted units, as well as some of our panel mount displays. So without further ado, let's dive right in. We're going to start by going over some general differences between explosion-proof systems, intrinsically safe systems, classifications that safety engineers look at from the gas and liquid areas, and then dive into intrinsically safe system calculations, and finally some labeling by FM, ATEX, and some of the major worldwide players. So the why do we care, or the so what for intrinsically safe system design, is to avoid the issue where we have, say, a grain silo here, and then after event from an explosion. So this is what we want to avoid to keep everybody safe, property safe, life safe, and all of the above. And there's two ways that we can go about that. One is explosion-proof systems, and the other is intrinsically safe systems, which we'll talk quite a bit about today. The main driver behind going to IS is cost. It's typically about 3 times cheaper for the complete project for IS system design versus explosion-proof. So what makes an explosion? You need really 3 legs of a tripod to have an explosion. You need a flammable substance, you need some sort of ignition source, and then you need oxygen. So this is why if you have a purged panel, they're typically purging that with nitrogen or some inert gas, so you're removing the oxygen from there. You can, of course, remove the flammable substance, but in most of the world that we live in, that substance is the product that you're working with, so that's hard to do. And finally, you can remove the ignition source. So anything like sparks or any heat that would cause an ignition to happen. So if you remove one of the 3, you're safe. And that is what we're looking at today. Here's a quick look at some sources of ignition. Some are quite obvious, like an open flame or a lit cigarette. Others you may not think about all the time, such as a static discharge, mechanical spark, and certainly hot surfaces can cause something to ignite. So these are things that can cause the ignition. Remember, we got to take away one of the 3 legs of the tripod there. Static electricity is one that happens quite often. You will see static discharge things when you walk into a sensitive area where you have to rub your feet on there to eliminate some of this or reduce the risk of it. However, static electricity, static shocks can happen just from a cold day when you reach out and you get that shock by touching a sweater. So the rules of the game are controlled by typically UL, FM, CSA, these sorts of groups in the North American area, by somebody like ATEX in the European area, or something like IECEX. And you may even have local standards where you live. And these groups all have fairly similar rules and things you need to follow, although there are some slight differences between them. The main thing that really catches people is what we call the different zones. So in North America, where I'm from, we'll typically say Class 1 Div 1, Class 1 Div 2, depending on the sensitivity of the area. Of course, if it's dust, we may say Class 2 Div 1, Class 2 Div 2. And then in Europe, where a lot of my colleagues sit, they will say zones, Zone 0, Zone 1, Zone 2. And this can trip up some people. We get quite a few questions about the difference between the ATEX and the North American standards. So what I've done here is we've got a quick, simple little gas station kind of diagram to give you an example. So in North America, Class 1 Div 1 would be all of the orange and red areas, whereas in Europe, Zone 1 would be the areas where something is likely that it could happen. So you're standing at the gas pump, for example. Zone 0 would be you really have to assume that there's a dangerous area there. And that would be something like inside the tanker truck or inside the tank underground. Zone 2 would be similar to Class 1 Div 2, which would be like the lighting up at the canopy at the gas station. Probably safe, but something could happen, so you need to be a little bit careful. So in North America, we call that Class 1 Div 2, and the Class 1 Div 1 we refer to as both Zone 0 and Zone 1. So there's a bit of differentiation in the ATEX standards that we just don't have in the North American standards. So here we're going to talk quickly about what safety engineers look at when they rate an area. If you're watching this and you're doing system design, you probably don't have to worry about this because the area is already classified as Class 1 Div 1, Class 1 Div 2, what have you. However, there are rules and reasons for that we want to just touch upon. So if you have liquids, bunker fuel, gasoline, some kind of chemical, you certainly need to look at the flash point. This is the temperature, so you can see gasoline, a flash point of negative 40 degrees Fahrenheit, whereas bunker oil would be somewhere closer to 125 degrees Fahrenheit. So this is the temperature at which the vapor can form an ignitable mixture. Your LEL and UAL, lower and upper explosive limits, refer more to gases. So certainly if you have something that's too lean to burn, there's not enough of it, you're probably in a safe condition. However, what a lot of people don't realize is you could be too rich to burn as well. So if you take propane, like you might have on your gas grill, if you have too little propane, of course, most people know it won't light. However, if it's too rich and too much propane there, so above 9.5% in this example, it also won't burn. So you can't have 30% propane and get it to light. You need to dilute that with air. And the reason is simply the molecules are overlapping and they're not leaving enough room for the oxygen molecule to get in there, which of course, as we know from the tripod, is one of the legs that we have to have an ignition. So the reason that people worry about hydrogen, you can see the range here is quite wide, 4% to 75%. Hydrogen also is pretty easy to light off. So when we talk about lighting it off, as I say, it would be minimum ignition energy. And this is how much energy is required if you're in that area where you between the LEL and the UEL to actually have an ignition. And you can see for hydrogen it's 17 microjoules, so quite a small amount of energy. About 1 joule is about what you get out of a spark plug. And then when we're talking about static electricity, that cold little shock you get from touching a sweater or a rug on a cold day, that's typically in the millijoules. So microjoules are quite small and certainly something that would be available in any kind of plant environment. So we will take these different things like the explosive limits, the ignition energy needed to ignite that, and they're going to classify the area based on a grouping. So you might see something like 2A, 2B, or A, B, C, D, Class 1, Div 1, Zone 2, Group B. These are things you will see on labeling for different products. And now you know a little bit about where that comes from. I don't want you to really worry about making those ratings because that's not the point of this presentation, but you should know where those different ratings come from. So, and then temperature, surface temperature is another one. So obviously if a surface is very hot and you pour a liquid on there that's quite easy to light, like carbon disulfide, the CS2 is going to light up pretty quickly. It's going to catch on fire just from a hot surface. So we rate those based on temperature classifications. So T1 to T6, T6 would be the strictest, which is a max surface temperature of 85 degrees Celsius. So you can imagine quite a few processes where that's just not possible. However, with things like electronics and a panel, like what we're dealing with the PR products, certainly 85C T6 is something you should be able to meet. But depending on the area, you're also going to have a T rating or a temperature rating. So here you can see different gases, flash points. You see CS2 there on the bottom at 100 degrees Celsius. So certainly you would need to be in a T6, maybe a T5, but typically a T6 for if you have CS2 around. If you're working with propane, certainly you could be a little bit warmer, maybe a T2 or above. So anything safer is always approved as well. And here's a few more ignition temperatures and T ratings for things like dust and powders. So what are you dealing with? What area are you working in? What's in the environment? What's in the area? What gases? How hot? These are all things we have to look at when they classify the area. So the ways we protect, one is non-sparking. We're not going to talk too much about this. This would be things like some instrumentation, certain enclosures, lighting fixtures that have a non-sparking, meaning there won't be a spark. There won't be that ignition source. And I'm going to say this 20 times during the presentation, but those 3 legs of the tripod, one of those is the ignition source. So if we take that away, we're safe. Another is a flame-proof or explosion-proof concept. You'll hear this called. And the point of this is you have a housing. You've probably seen these panels. They have lots and lots of bolts. If they're screw-on caps like you see on our field temperature transmitter here, there's a lot of threads. You got to keep screwing that thing down 20 times or so. And the whole idea here is that if an explosion or an event happens, it will be contained within the housing. And by the time the gas gets through all those threads or seeps out, it'll be cool enough that it won't be a danger to the surrounding environment. So this would be explosion proof. You need special conduit fittings, you need special cabling. It does require heavy, either lots of threads or lots of bolts, so heavy enclosures, and all of that adds up to cost. Project pricing can be quite more expensive with explosion proof design versus intrinsically safe design. So now we're going to dive right into intrinsically safe design, which is the point of this presentation. So what is the intrinsically safe concept? Basically, what we're saying is that we will not allow enough energy out into the loop, into the hazardous area, that will create an incident. So if we need an ignition source and we know we need something to ignite, we will not put enough energy out there that transmitter, that device, that unit that's sitting in the hazardous area has a chance to have an ignition. And so the unit itself is going to be rated by 5 entity parameters. And then, of course, the barrier itself is going to be rated as well. And we need to match those up. So it's not enough to have, and we hear this quite a bit, I have an IS device in the field. That's great, but that's only one of the 3 things you need to look at. You can have an IS device out in the field that's perfectly safe under proper operating conditions, and then you dump 5 kilovolts out there into it, and of course there's going to be an ignition. It's not rated for that. So you need to have something, which is the IS barriers that we sell and others, but you need to have something that's limiting the amount of energy to at or below what that unit is rated for. And then of course you have to look at the cabling in between as well, because that could hold a capacitance. So there's 2 main types of IS barriers. One is called a Zener barrier, and this is simply a diode that's connected to a ground. And when the amount of current, voltage, power, energy, we say, gets over a certain limit, it's going to shunt directly to ground. These are an older type of device. They're typically a bit cheaper. However, they're simply a diode connected to a ground. And if that ground connection is ever severed or damaged, then you're possibly failing in a dangerous state. So these have been frowned upon. You'll still see them grandfathered in. You'll still see them used, but a lot of facilities are starting to not allow these devices because they could fail dangerously. Galvanically isolated barriers, which is what PR Electronics makes as well as other companies, work a little bit differently. These are isolated barriers, so you add in isolation from ground noise and other types of signal interference, but they also don't need to be grounded, so you don't have to worry about a ground connection going down. If they do fail, you'll have 0 energy in the loop, so the unit won't work, but you're going to fail in a safe state. So this is the main driver behind galvanically isolated barriers. So I mentioned the entity parameters. These are the main 5 that you will see listed on, or they have to be listed on every IS device, whether it's the transmitter or the system out in the field, or whether it's the barrier itself. And what we're looking for here is that the barrier is putting out the maximum or less than the maximum that the unit is rated for on all 5 of these parameters. I'm going to go through that real quickly. So here we have a temperature sensor, a thermocouple in the field, and you see 30 volts, 120 milliamps, 0.9 watts, on and on. And then we have the barrier itself. So what we're looking for is the barrier less? Yes, 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 on power, on voltage, current, and power. So we're good there. However, for impedance and capacitance, we know that the cable itself can hold a charge. Think of a cable coiled up in the bottom of your panel. That can certainly act as a capacitor. So we need to take that into account as well. So we're going to do some quick calculations. PR or any of your IS barrier manufacturers can help with these to look at the maximum length of cable you can have between those 2 devices. If these 2 devices match and the cabling works out, then you have an intrinsically safe system. If these do not match, meaning that if this is going to possibly allow more energy out into the field than it's rated for, you are not safe. And you need to use a different barrier, or you need to use a different sensor or product out in the field. So all 3 of these need to be matched to be an intrinsically safe design, and that's pretty critical to this whole presentation. So I'll say that one more time. All 3 of these need to be accounted for and to match. The sensor in the field, the barrier itself, and the cabling in between. It is not enough to have simply an IS device sitting out in a hazardous area. That does not make you safe by default. Of course, a quick ad for PR Electronics here. When you're worrying about what gas zone and what classes and T rating and all of these things, you don't have to worry about that with us because we meet the strictest requirements on all of these. So you just need to make sure that the IS barrier is matched to the transmitter from an entity parameter standpoint, and you're good to go. So real quickly on labeling, because this can bore you to tears, you will see a lot of letters and codes and things like this. This is what they mean. If you have questions, you can certainly ask us about it. You will see this marked on all IS or hazardous area rated units. If you do not see this, that unit may not be rated, probably is not, and you need to double check that. The one exception would be things like temperature transmitters, hockey pucks, which are kind of small units. So here you see an example. The smaller units just don't have the space on the label to put all the information. So ATAX, FM, they do allow for a smaller version of the markings on the label, but you still will see something there. And then, of course, in the manual, we'll have to list out the entire rating. So here's a range of IS barriers, some of our IS barriers by PR. Certainly, we cover thousands of applications with these 6 products alone, so it makes it quite easy for specifying things. Of course, you get the galvanic isolation, so you're avoiding a lot of noise. You've got things like signals going from the hazardous area or signals going into the hazardous area, driving solenoids, pulses, digital pulse waves, and then, of course, temperature and universal systems. Here's some additional temperature. So let's go through these examples pretty quickly. These are kind of interesting, but your example will not be exactly one of these, I'm sure. But here's a pressure application. So we have a pressure transmitter sitting in the hazardous area. We're going to a barrier sitting in the safe area. We need to repeat that to a PLC that's controlling a gas shutoff valve. So you need to have the barrier matched with the sensor. And then, of course, you see the baby blue terminals here. That is at least the US North American electrical code for IS wiring. So the wire itself and then the inputs from the hazardous area should be that blue color. Here's another system where we are actually sending the signal into the hazardous area. So there's an I to P converter that's controlling a valve, and we need to send from the PLC through the barrier out into the hazardous area a current signal that's going to change the valving. Another one, a crude oil tanker. You've got a loading arm. You may be doing a limit or a position switch for safety. Certainly you will be controlling that arm by some sort of a joystick PLC controller, but there'll be a limit switch there. So if it goes outside the range where it should, it's going to trip something and stop that movement. So in this case, it's a switch. So it's an on-off kind of relay setting coming through from the hazardous area. But again, that also needs to be run through a safety barrier. And here's a temperature application where we have a thermocouple sitting out in the field, and it's feeding that temperature straight into a barrier. The nice thing about galvanic barriers is they could do, as I said, more than a Zener. They're not just an IS. So in this case, we can accept the thermocouple directly and then export a 4 to 20 milliamp signal. So we can do signal conversion as well. So any questions on this, please reach out to us. We're happy to help, as I'm sure are other manufacturers. But hopefully this gave you just a quick taste of intrinsically safe system designs and some things to watch out for. Thank you very much.